In the previous section, we looked at sequences, which we just viewed as infinite lists of numbers. And we answered some questions about convergence of sequences. So we have an infinite list of numbers. Are those numbers heading towards a particular place? In this section, we're going to look at now adding up all of those numbers in the sequence. And these are what we're going to call series or infinite series. So suppose we have a sequence of numbers, which we'll call an. We're going to write down expressions of the form a1 plus a2 plus a3 plus ... to indicate that we're going to add all of the terms of the sequence together. And we're going to call this an infinite series. It'll be convenient to use our sigma notation or our shorthand notation for these sums. And so we're going to use sigma from n equals 1 to infinity of an to denote the series a1 plus a2 plus a3, etc. Now sometimes we'll use this shorthand notation where we omit the limits on the summation symbol. And this is, again, just to represent the fact that we're summing the terms of a sequence. So the sequence an should be defined, and now we're just going to use sigma of an to denote the series. At this point, we may be concerned that, well, it doesn't make sense to add up infinitely many numbers, because if you add up infinitely many numbers, then you'd expect the result to be infinite, because each time you're adding something to it. So obviously, every time you add something to it, the number gets bigger, and then bigger, and then bigger, and then bigger. And so eventually it becomes infinite if you add infinitely many numbers together. Well, not necessarily, and we'll see some examples of this. But what that sort of line of thought tends to indicate is that we really need to have a definition of what it means to add infinitely many numbers together. What we mean by that in terms of the resulting sum. So it's no problem to add finitely many numbers together. So let's start with that. We'll look at the nth partial sum of the infinite series. And the nth partial sum we get by just adding the first n terms of the sequence together. And we'll call that result s sub n, or the nth partial sum. So the first partial sum, s sub 1, is just a1. The second partial sum is a1 plus a2. The third partial sum is a1 plus a2 plus a3, and so on. Now what we have here is, if we look at these partial sums, this forms a sequence, which we'll call the sequence of partial sums. So you see what we did there? We took this new problem involving sums, and we now converted it to a problem about sequences. So we start with this sequence ANs, we construct this new sequence of partial sums where the first term of our new sequence is just the first term of our old sequence. The second term of our new sequence is the sum of the first two terms of our old sequence. The third term of our new sequence is the sum of the first three terms of our old sequence, etc. And so now we can ask the question, does this sequence of partial sums converge? Do the SNs converge somewhere? If it does converge to some number, then perhaps that's a reasonable definition for the sum of the series. So this idea of adding up infinitely many numbers, we've tied now to a question about convergence of the series. Okay, so at this point I just want to play around with series, and I'm going to use Wolfram Alpha to do some calculations, and let's just see what kind of interesting things could come up from studying series. So let's look at the series 1 over n squared as n goes from 1 to infinity. Again, you may think that, hey, you're adding up infinitely many numbers, so the result should be infinite. Well, let's see if that's actually the case. And we see that the result is pi squared by 6. So the sum from 1 to infinity of 1 over n squared is pi squared by 6. What does that mean? That means if I was to look at the sequence of partial sums, where the first term of my sequence is the sum of the first term of the series. The next term of my sequence is the sum of the first two terms, and then the next term is the sum of the first three terms of this series, and so on. And I construct these sequence of partial sums, those s sub n's, then that sequence is going to converge to pi squared by 6. So the more terms I add up in the sum, the closer I get to pi squared by 6. And if it were possible to add up all infinitely many terms, then I would get exactly pi squared by 6. So let's try another example. Here I'm going to look at the sum of 1 over n factorial as n goes from 0 to infinity. And we see that that sum is e. So we can recognize e, the natural number, which seems to come up in calculus quite a bit. For example, it's the base of the exponential function whose derivative is itself. It comes up here in series as well as the sum of the series where the terms are 1 over n factorial as n goes from 0 to infinity. So what this means is that I keep adding terms of this series, 1 over n factorial, where n equals 1, n equals 2, n equals 3, and I keep adding more and more and more terms, the closer and closer and closer I get to e. The more terms I add, the closer I get to e as the sum. And if it were possible to add up infinitely many terms, then I'd get exactly e as the result of the sum. As a final example, let's just look at the sum of negative 1 to the n over 2n plus 1 as n goes from 0 to infinity, and let's just throw an extra 4 in front just for fun. And we ask Wolfram Alpha to compute the sum of that series, and we get a value of pi. So that's interesting. Pi, which we normally think of as being related to trigonometric functions and trigonometry, here it comes out as the value of an infinite series. We'll actually see later on why pi comes out as the value of this series, and it has to do with the fact that this series is related to a trigonometric function. But we'll have to wait until we get to the later sections of this chapter to make this connection. So at this stage, we've just had a little bit of fun with Wolfram Alpha, and we've computed some values of some series. There's some other ones that I didn't do with Wolfram Alpha, but you can try them yourselves. How about the sum of 1 over n? Well, it turns out that that diverges. Fire it into Wolfram Alpha, see what it comes out as an answer. Ask it to sum from n equals 1 to infinity of 1 over n, and it'll come back saying that the series does not converge. So, of course, this in some sense was to be expected. We don't expect all series to converge. If I add up infinitely many numbers, it's a possibility that the sum just keeps growing and growing and growing and growing. What is a surprise with this one, though, is that our terms are actually getting small. Like the one above, 1 over n squared, those terms are getting smaller and smaller and smaller. So when I keep adding them onto the end of this series, keep adding more and more of these 1 over n squareds onto the end, I'm adding a little bit, and then a little bit more, and a little bit more, but those 1 over n squareds are getting small as n gets big. So we're adding only a tiny bit at the very end. And it turns out that since this sequence of partial sums converges to pi squared by 6, that these things I'm adding onto the end don't contribute very much. And so we get this finite value for the sum of the series. But for this one, the sum of 1 over n, it looks like there is a significant amount being added onto the end each time, which causes the series to diverge. And we'll investigate this one in a little bit more detail later on in this section. Let's now summarize what we mean when we say a series is convergent. So we have an infinite series, sum of I equals 1 to infinity of these terms of the sequence ai. Let Sn denote the nth partial sum, and so those Sn's form a sequence. And we can ask our questions that we've been asking about sequences all along, and that is the sequence convergent or divergent? If the sequence is convergent, and let's suppose that the sequence converges to S, then we say that the corresponding series is convergent. And we write then that the series is equal to S, that the sum of the series is equal to S. And we call S the sum of the series. If this limit of the sequence of partial sums does not exist, then we say the corresponding series diverges. So let's look at an example. Here let's consider the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. Notice each time the next term is 1/2 of the previous term. And so we can ask, what is the sum of the series? Does it exist? Does it converge? Does this series converge to some value? The more terms you add, the closer you get to this value to which it converges, or is this series diverging? Well, let's just get an idea for what's going on with these terms. So what I'm asking here is to look at the sum of 1 over 2 to the k as k ranges over values from 0 to n. And let's construct a table of all these partial sums. So what comes out is we've got the sum of the first term is just 1. Sum of the first 2 terms is 1.5. Sum of the first 3 terms is 1.75. So here's our sequence of partial sums. And we look down the list, and we see that as we compute these partial sums, the sum of the first 20 terms is 1.999. And it looks like these things are getting closer and closer and closer to 2. So how do we know that the sequence of partial sums actually gets closer and closer to 2 and doesn't just jump past 2 and maybe they're on their way heading to 3 or 4 or something like that? Well, the problem is just calculating the first 20 values or the first 100 values or the first 1,000 values generally doesn't give us the full picture. We need some other argument that tells us exactly what's going on. And so what's the other argument that we can do? Well, as we'll see shortly, we're able to come up with a general formula for the nth partial sum. It turns out that the nth partial sum is 2 minus 1 over 2 to the n minus 1. And we're going to see that in example 6 below, in the much more general case. But for now, the nth partial sum, so the sum of the first n terms, turns out to be 2 minus 1 over 2 to the n minus 1. And so we can see now that as n gets big, as n goes to infinity, this piece, the 1 over 2 to the n minus 1, that has to get small and go to 0. And so the nth partial sum has to head to 2 as n goes to infinity. So that's essentially how we find the sum of a series, is we look for some pattern giving us the nth partial sum, take the limit as n goes to infinity, and we'll get the value of the series.